if life got started on Mars but then went extinct, what was the fundamental shift in the planet's evolution that drove that to happen? Or if it's still alive, of course, that is a paradigm shifting discovery, right? Confirmation that we are not alone in the universe.
So yeah, I'm here with Dr. Amy Williams of the Geological Department.
Geological sciences, yep.
Full professor,
Assistant professor, yep.
Tenure track. Yeah, so thank you a lot for this conversation. So we're just talking, and that I think it's very important for these conversations because you get to know that the other person at least more deeply than a normal quick interview. So on that note, I wanna ask you about your early career. Like, how did you started thinking about these problems? When did you start thinking? What interested you in them? And yeah, like, was there like moments that sparked that curiosity into this crazy field? Because it's not, as you said, it's not really a mainstream field, maybe, or not mainstream in the term. It's not like a normal thing that people go. It's like, oh, I want to go to geology, right? It's like a cool niche thing that is like difficult to find, right?
I would say what I do now as an astrobiologist and a geobiologist, I feel like that's almost more niche at this point, and even those are becoming mainstream. So I mean, geology is one of the four big sciences, right? Physics, chemistry, biology, and geology, and I feel like so often geology is left out of that story, and it's just so fundamental, at least in the way that I explore all of the sciences together in a multidisciplinary way as a scientist. I find that geologic knowledge, it really enriches the way that I can think about physical systems working and evolving. So it's important to me that people know that geology is a science, that it is an option, in school to learn about. Not that you need to major in it necessarily, unless that's your passion, like it has become for me, but that it's one of the pillars of the hard sciences that I feel like gets looked over sometimes. And it's just so, it really does, I feel, enrich the conversation when you talk about physical processes on Earth and on other worlds, which is where my whole line of research has ended up going.
So what exactly is it? You started talking about it, the study of physical processes, but what are those processes? Why are they important? And yeah, what do you think it makes your experience of sciences more rich?
Yeah, so I mean, when people hear that you're studying geology, for example, when I was in college, they said, what are you going to do? Learn about rocks? And it's often said almost in a joking way, like, well, that's not real science. But, geology is so much more than just the rocks, right? It is the chemistry of the entire Earth. And it's not just that, but it's the physical processes and tectonic or planet-wide processes that enable Earth to be this habitable world where life has been able to evolve and thrive. So on Earth, one of the major studies of geology is tectonics, or the way that the thin kind of plates on the surface of the Earth move around in response to basically these big changes in heat and energy from our mantle and from our core of the Earth. And so because we can have things like mid-ocean ridges that are spewing out new rock effectively, and they're kind of pushing plates apart. And then we have these regions where plates are actually subducting underneath other plates and going back down into the mantle. These processes, I don't think people get the opportunity in primary and secondary school very often to learn about this, but they are fundamental to how the Earth functions as this dynamic planet. And, many people argue it's one of the reasons that Earth is habitable, because you have this cycling of elements, cycling of chemistry from this really large scale process that potentially allows life to thrive on Earth the way that it does.
So, and that can spark a conversation of, is that a needed thing for other planets? Because you're studying Mars, and I imagine Mars have at least some kind of similar dynamics of plate tectonics or something like that. Not really. I'm just talking about my.
Yeah, no. So I mean, this is that you're hitting right at the point that people are trying to understand what different factors are required to make a planet habitable, to make it really reasonable for life to survive there. And so while we think that Mars had plate tectonics very early on in its history, those tectonics have effectively shut down. And in part, that is because so Mars is much smaller than Earth. And the geodynamo is kind of the term that we use to describe the circulation of a planet's core, which is going to generate a magnetic field. And it is the dynamics within that core and the mantle and kind of circulation of energy within the mantle that allows plate tectonics to function.
Okay.
And so if you have hot material upwelling, that is going to eventually break through the crust. And when that happens, that material, it's rock, right? So when it reaches basically a surface that's much colder and lower pressure than it was when it was inside the planet in the mantle, it's going to cool off and form rock. And so in order to maintain the same size of the planet, basically, if you're making new rock in one place, you need to recycle or remove rock in another place. So that is the sort of the fundamental basic level of plate tectonics. But on Mars, we don't see active plate tectonics. There is no magnetic field. So we believe that the geodynamo, so that circulation of the core inside of Mars, has slowed down or stopped in a way that it's not driving plate tectonics anymore. There's no magnetic field anymore. And then that actually really speaks to the big problem of habitability, modern habitability on Mars, because there's no magnetic field to protect the planet from solar wind, which means that your atmosphere gets blown away. You have much higher radiation fluxes to the surface, which
from
can
the sun
be
or other sources.
Well, galactic cosmic rays, solar winds, the whole 9 yards. And so that ends up being, it makes, as far as we understand life, life as we know it, it makes for a very challenging environment, at least on the surface of the planet.
Right.
Yeah.
Right. So, and to answer all these questions, we've figured out a way to send vehicles and into the surface and, of course, into the orbit. So that maybe is a way to introduce curiosity and perseverance that you've worked with for a couple of years. So I'm interested in, what do you think those are important, and why spend all these resources studying, like the question that it's on a lot of people's minds, like, why spend all these resources studying another planet where you can spend them here? And also, when you cover that, like, why Mars specifically?
Oh man, so many things to speak to there. So first off, I've had the opportunity to work on NASA's Curiosity and Perseverance rovers. Really extraordinary opportunities, and I definitely recognize that. I joined the Curiosity mission in 2009 as a PhD student myself, and now as a researcher on both of those missions, I have the opportunity to help the PhD students working in my lab join the missions as well. And so that is very fulfilling to me on a personal level to enable that and hopefully open up opportunities and avenues for those students to build their planetary science careers, in some of the ways in which I've had the opportunity to do so as well. So for the missions, I've been on both missions since the beginning for both of them, which is a unique opportunity, and I've been trying to basically like give as much of myself, my professional resources to it as possible, because it is so extraordinary, and we do have the opportunity to make incredible fundamental discoveries, not just about, one of our nearest neighbors, planetary neighbors, Mars, but the information that we get from that actually feeds into a better understanding of Earth and of the inner rocky planets, how they formed, why they're different. One of the things about Mars that's really striking to me is that, the inner rocky planets, they all formed at the same time from similar processes, but they are so extraordinarily different from each other. And Earth and Mars, start out so very similarly. And then their planetary evolution just diverges so greatly, right? In Earth, it, becomes this not only habitable, but inhabited planet. And we have those questions about Mars. We know it was habitable in the past. We know that there was water. The question is, was it ever inhabited? And is it still inhabited? And that really speaks to sort of the core of at least Martian astrobiology and the questions that we want to learn about that. If life got started on Mars but then went extinct, what was the fundamental shift in the planet's evolution that drove that to happen? Or if it's still alive, of course, that is a paradigm shifting discovery, right? Confirmation that we are not alone in the universe. And, as a kid, I always kind of pictured, looking up at the stars, that someone was out there on a world somewhere looking up at the stars in their sky and thinking, I wonder if someone is out there. And so the two of us thinking this at the same time, light years apart. And so, to that little girl who was thinking those things, me as a child, this is really fulfilling to be able to try to answer these questions with these missions. And right now, the technology that needs to be developed to send humans to Mars, we're working on that, but it's significant. It's substantial development to send people and to bring them back. And so, as we develop our technologies to enable that, we are also that feeds into the technologies that build these extraordinary rovers that we're able to send, not only to Mars. I mean, we send missions to other worlds as well. But Mars is relatively close in the grand scheme of things. And because we've had the opportunity to explore it a decent amount, we are more advanced, I would say, in our technologies to land instrumentation, rovers, and missions there, and to learn more about that world. We started in the 70s, even before the 70s, but the Viking landers were the two that landed in the 70s and kind of started our in situ exploration of these worlds.
And it's very funny about the girl looking at the stars, because it really is a paradigm shift to find another life, even if it existed millions of years ago.
Mm-hmm.
And because I don't think people realize the how long has Earth and Mars has been here, or at least since the creation of the universe, the Big Bang. So there has been a lot of time for life to develop, right?
Yeah. And we really think, I mean, you said millions of years, but truly we're looking on billions of years time scales. Yeah.
Yeah, and I think that really is an interesting question. And is that the motivating factor? Is that when you've met people that are working in curiosity and perseverance, is that one of the main motivations of just like that philosophical curiosity to figure out whether we're alone or not and the implications of that? And yeah, because I would imagine like you could say, oh, this is cool, or maybe I'm making good money or something like that. But yeah, like I want to push more on why this is important for you why this is important for the people that are doing this.
Yeah. So, I do get that question, like, are you investing resources in something that's sort of pie in the sky, exploration for the sake of exploration? Mm-hmm. And I would push back on that and say that it's not that those resources are going to go to something else in the some other purpose, right, on Earth. And we do get that kind of pushback sometimes, but the point is that it's not an either or.
Yeah.
That exploration and scientific inquiry and understanding of the natural world is vital to the survival of not just humanity, but basically humans are able to impact the world in a way that other species have not been able to do so since effectively the evolution of photosynthesizing bacteria, which did fundamentally change the atmosphere on Earth billions of years ago. So it's not just the survival of humanity, but it is our responsibility to be responsible stewards of the Earth. And so in my mind, that goes to understanding not just earth science, environmental science, and core sciences, right? Physics, chemistry, biology, geology, but to understanding that on other worlds as well. And so again, you can learn so much about the evolution of a planet by studying it in the way that we are able to with Mars and with these missions, with Curiosity, Perseverance, the missions that have come before, and especially the missions that are upcoming. So these resources that are invested in these missions, it sounds like a lot to say $2.5 billion on a mission, but if you look at where $2.5 billion is spent by any global economy.
Yeah, basically
around the world,
there's plenty of money around for this thing, and even if it's just exploration for the sake of exploration, I think that even is a noble thing to do, like just exploration, just to push the boundaries of what's actually possible for civilization. Like what else? How cool can you get more than that, right?
There's a cool factor, absolutely. I mean, I think that I think that the scientists who, and engineers, the whole team who participates in this kind of work, we do owe it to everyone. It's not just about exploration, right? It is science. It is about pushing the boundaries of science.
Yes.
Because science is the way for us to move forward, the way for us to survive. And it's important for us to understand our natural world, and that extends beyond just the atmosphere of the Earth, right? Our natural environment is the solar system, is the galaxy, is the universe.
Right. And and if you care about life, you would probably care about what happens to human life over the course of millions of years, and understanding how life originated might be a good way to figure out how to keep life alive, right, over millions of years. Because I think when you look at the big picture, maybe Earth is fragile, and we should for sure preserve it, but I would say it's smart to have a plan B just in case, right? And understanding what happens in other planets, how life originated, it's a way to maybe make sure that we can continue our journey, and we can continue being humans, even if it's in just other planets, or in Earth and in other planets at the same time. I think, I think looking at it's still important to look at the big picture. Definitely, it's important to look at what's happening right now, but as you said, it's not a either or. Like, we need people looking at problems right now, and we need people looking at problems.
Solutions for the future, right?
No problems in the future. Solutions for the future.
There'll always be problems in the future, right? Exactly. Yeah. And I think that people, I get a lot of questions about, when are we going to colonize Mars? And I'm like, that is so far ahead, if it is possible, right? Like exploration is one thing, right? People explore Antarctica, for example, right? What we would deem for humans to be an extreme environment. And yes, there are a handful of people who live there year round in order to keep facilities going, but it is a handful of people because it is a very challenging place.
Yeah.
And without resources being brought in from the outside, effectively for humans, it's not a habitable environment.
At all,
and I think that
and Mars is worse.
And Mars is far more challenging. You can't breathe the air there. So, it is So I appreciate taking the science that we're doing, the exploration, technology development, and the concept that maybe we can become an interplanetary species. But we are so far away from that. And one of my concerns truly as a scientist is that if people don't place value in the science we're doing today, how do they think we're going to get to the science of tomorrow?
That's fundamental, right? Yeah. And even when we get to Mars, we would still need people studying other planets. And maybe, now we're here on Mars. Maybe we want to go to Jupiter's moon, or we want to go outside of the solar system. So, science will never be not important.
Right. Yeah. It'll never be done. Right. There's no end point. Like, all right, the science is done now. The science is never done.
And it's cool. So we can stick on Mars. We've already been with a couple of rovers. We've sent no more than 10, but somewhere around that number, right, of rovers with Curiosity, Sojourner.
Not even 10. At least
5.
U.S. Yeah. So Sojourner, the Mars exploration rovers, Spirit and Opportunity,
right,
Curiosity, and now Perseverance. And we have several landers, right, that don't have mobility capabilities, but landers are a much more cost-effective way to send something. If I land here, I can do the science I need to do. But rovers, they give you so much more flexibility to accomplish the science that's part of your primary mission.
Right, and that's basically what you need, right? Because at least for your research, I would imagine you would definitely need that ability to move around, to explore different points of interest, and based on what you want to discover, right? So I found it really interesting that yours was. I want to ask you, like, for Perseverance, was it that they landed specifically in the place that has the delta, or they drove to the delta? And maybe you can explain what the delta is for people that have no idea.
Yeah. So Perseverance is it serves two purposes. One is to explore this location you were talking about, Jezero Delta, and inside of Jezero Crater. And I'll define a delta in just a moment. But it's not just to explore, just to see what's there.
Yes.
So each of these missions, we especially for the cost, but also to accomplish the best science that we can in the lifetimes of these missions, we have certain mission goals, right? The prime mission for Perseverance is to look for geologic units that might be able to preserve evidence for ancient life on Mars.
Okay.
So not modern life, but extinct or ancient life. Yes. So that's one of the big goals of this mission. And we sent it to Jezero Crater because it has this delta in it. And so a delta is a name for a geologic formation that forms when a river is flowing into a lake. And so you can picture the muddiest river you've ever seen. If people have seen the Mississippi River, right? It's basically mud colored because it has rocks and silt and mud within the water column. And so when all of that material flowing in a river flows into a standing body of water, like a lake or the ocean, in the case of the Mississippi, you can imagine the velocity of that river slows down suddenly. And that water, starts to fill into the basin, and the sediment that was in the water column settles out. And so it's going to deposit on the ground, ground being what's underneath the lake surface. So these structures, they're called deltas because they actually, in some cases, actually look like the Greek, delta shape.
Oh, I didn't make the connection.
Yeah. So like the triangular shape. And these deltas, at least on Earth, are habitable environments, right? You have an influx of nutrients, you have water, you have, at least on Earth, a source of organic carbon. And so those are kind of the big things needed for life to survive on Earth. And so we use our knowledge of life on Earth and life as we know it, and leverage that to say, what's a really good environment to search for evidence of ancient life on another world. And so because the geology of Mars is actually quite similar, except for the lack of plate tectonics, geology of Mars is quite similar to Earth, we can use these principles of uniformitarianism. Basically, what happens today it's the same processes that were happening even in the ancient past. And so we use those principles to say, okay, this delta on Mars, we know it was formed by a river flowing into a lake, and we know where to look for evidence of life in deltas on Earth. So let's leverage that information to search for that evidence of ancient life on Mars in Jezero.
And I think that's wonderful, right? Like how can you study something that happens here on Earth, apply the same principles on another planet, and figure out the past of that planet? That's just wonderful, right?
Yeah.
I think, and maybe like the whole science process as a whole of, how do you describe it? Like compare one environment with the other and just assume that the rules are the same. And just by knowing the rules, you can get this whole log of how things have, not only what happened in one specific moment, but how things progress.
That's right.
And you can see like the history like play out. It's like a video that's almost like, that just like a
time lapse.
A time lapse.
Yeah. So I mean, you have just like perfectly encapsulated why geology attracted me as a student, as a college student, because I discovered for the first time that you can look at a wall of rocks, an outcrop of rocks made of, for example, sediments. And I can basically read each layer of that rock like pages in a book. I can reconstruct in my mind what happened in that environment millions, billions of years ago, because those principles are the same for why those rocks deposited the way they did and what environments they represented from the past. So that was like what drove me to join geology, take it on as a major, and pursue it as a career, because you can learn about the ancient past in excruciating detail just from looking at rocks. I mean, that's pretty incredible.
Yeah, it's pretty incredible. And leveraging that with the knowledge of how life evolves, because you would not only know how rocks have transformed and evolved through time, but only you need to understand how life evolves, right? And what are the conditions. So maybe you can touch on, how do we know that those three components that you mentioned, why are they important, and why do you think, why are they important for life? So assuming that there was life in Mars, what would finding these components might be an evidence of?
Yeah. So, the generalization for what at least microbial life, so like our bacteria and archaea on Earth, that's sort of what we're looking for on Mars at this point. I imagine if there was dynamic macrofauna, it would have introduced itself to us at this point on Mars, right? So I'm not looking for
macrofauna. Do you mean like maybe some
animals?
Tree? Okay.
Yeah, plants, animals, large can be the size of an elephant, or it can actually just be the size of a multicellular microbial organism, right? So it can still be extraordinarily small from a human perspective.
Right. And I don't think we found elephants in Mars yet, right?
Exactly, right? So the fact that it's been challenging to find evidence for life on Mars thus far, indicates that it's not prevalent if it is there. Or it's somewhere we haven't been able to explore yet. Okay, so two different things you have to address with that. But certainly we only have the one data point for life, and it's life on Earth, right? And so just like with geology, we need to take what we know and try to apply it to, how do you search for life beyond Earth? So we say, okay, let's take what we recognize as a bias towards terrestrial life, the things that it needs, and let's apply that to that search beyond Earth. And on Earth, what life needs is water as a universal solvent. It needs an energy source. So that can be sunlight, or that can be chemical energy. So basically reduction and oxidation processes, or what we call redox. So chemical energy. and then it needs carbon.
And
so all life on Earth is
the
carbon-based.
redox processes could come from the energy inside the core of the planet.
Oh no, not even like that. No, just changes in redox state of minerals. So there's entire suites of organisms on Earth that basically eat rocks, and that's where they get their energy from.
Oh, cool.
Yeah. So all of that, and then carbon as sort of the third pillar on the stool of things that you need for life, right? You can sit on your little like bench stool or lab stool, and it's got the 3 legs, and that's what I really picture it as: carbon, water, and a source of energy for metabolism. And so using those, the search for those 3 in environments on Mars is a really good starting point for how do you look for an environment where life would want to have lived in the past, even if that life isn't there today.
Right. And real quick, for the carbon and the water, carbon is just because life, as we know it here on Earth, is mostly made of carbon.
Correct.
And water, because if you take water away from most of organisms, I imagine that there's some exceptions, but if you take that, it dies.
Right. Water is required to maintain basically the chemistry within a cell.
Okay.
That's because water is present on Earth. That is how life on Earth has evolved to regulate its homeostasis, right? By balancing the concentrations of solutes and water within a cell relative to what's outside of it, outside of the cell. So that's where, our expectations for Terran life really color our search for life on other worlds. Now, if you go to a world like Titan, where you have lakes of methane and ethane, so, organic carbon is now the solvent. One of the big questions is what would life look like if that was its solvent instead?
Right.
And so these are huge questions, and NASA's sending a mission to Titan in
and
the
Titan
coming
is
years.
One of Jupiter's moons.
Yeah.
Okay.
So I'm so terrible at remembering this now. When it comes to outer worlds, I'm so bad about it. I'm being like I say the outer worlds, and I don't specify because I lose track of which. And I mean, they're basically planets orbiting these gas giants, right? We call them moons, but they're effectively their own worlds unto themselves.
And they're almost Earth size, right? I think at least Titan either is almost as big as Earth or a little bit bigger, maybe,
and I don't remember the details. Yeah, but Europa and Enceladus come up as very intriguing outer worlds because they have these liquid water oceans. So again, playing into our not only desire but also, I mean, it makes sense, like, look for life that looks like what you know, right? And then you can expand out from that and say, what would life look like that doesn't look like Terran life?
Yes.
Could there be life on Titan? What happens with these organic solvents instead of having water as a solvent? Those kinds of questions that are further out there, but are still questions that we're asking about astrobiology and the search for life beyond Earth. How diverse is it? What's its ability to use different kind of building blocks, or building blocks that are different from life on Earth as we know it?
Yeah, because it's very weird, right? Because we haven't found any other signs of life from other planets. But it might be because we're looking at things in the wrong way, right? We're making the wrong assumptions. Maybe we are, maybe we're not. So at least that adds to the complexity and the interesting part of the problem, right? How do you approach finding something that you have no idea? You've only one sample size.
Yeah.
Right. So you have no idea if it could have evolved from way different conditions with way different elements. Maybe it doesn't even have to be carbon based, right? Maybe it can be like silicon based or something weird like that.
People love to go to silicon based life. Yeah. I mean, and there are all these ways to study the fundamentals of like basically chemical bonding. Like, why does it make sense that life would have to be carbon based? Why is it actually a challenge to have silicon based life? And so there are fundamentals of chemistry and physics that do provide hard boundaries, as far as we understand, to the ability for life to evolve and for these chemicals to come together to form life, either as we know it or as we don't know it. But this is a major realm of study in astrobiology, is the study of life as we don't know it, and trying to force ourselves to face our Terran biases of what we expect life to look like and be like, and how we search for it, right? So when you send a mission to another world, you got to think carefully ahead of time what instruments are going to help you look for that life, and what assumptions are you making that life, if it is there, might surprise you with, right? Like, what if it uses different nucleobases in its DNA? What if things are just slightly different from on Earth in a way that your instrument that you sent to that world to look for life can't quite detect? And those are the kinds of things that I think about for my research and my interest in astrobiology. Like, how do you actually search for that life? And then how can you be confident if you think you found it? How can you be confident in that finding?
And I imagine the whole area of instrumentation can be its own rabbit hole. Of, like, complete of, okay, we have, like you were saying, we have this sort of assumptions, but we might like account for a little bit outside of what we know just in case. And you have to like bring everything together, right? You have to bring the conditions of the other planet, what you can physically bring to the other planet, the money that it takes, and the time that it takes to develop all this technology,
and the time to even fly to these worlds, right? Like when we go to Mars,
they're very far apart.
I mean, it's on the order of months, right? Like 6 to 10 months, depending on how much fuel you can use to fly. But I mean, it is an entire, it's basically a lifetime, or a career's lifetime, to send a mission to the outer worlds, right? So if I'm on a mission that's going to send something to the outer worlds, and like we're coming up with concepts and proposing it now, I'll be retired or almost retired by the time those missions make it to those worlds. Right. So these are multi-generational missions, meant to expand our knowledge of science, but it's not just like one person is the principal investigator seeing this through. It truly is the scientific community coming together to feed forward in making these missions happen.
Yeah, and I think that's wonderful, right? Also, just having this large-scale collaboration of people trying to achieve the same goal, people trying to work out their differences just to make something happen, and plan their time so that all the resources can align and just be able to do this amazing like endeavor. And it's very complex, right? I imagine like this collaboration. Maybe you can speak about how big are the collaborations. Like, I imagine you have to work with not only US universities and you have researchers, but also like international researchers.
Absolutely.
And yeah, like how is this dynamics between, how do you assign, maybe just briefly, like how do you assign work and who works on what? Like how maybe
sort of the architecture of how the missions are set up. Yeah, so it does depend on the scale of the mission. So Curiosity and Perseverance are both what we call flagship missions. These are the biggest, largest caliber, largest architecture, and so these are teams of hundreds of people, scientists and engineers. There's the people who built the rover and built the landing system. There are those people who are operating effectively, like the software that helps us drive the rovers and manipulate the arm to do science and to do all of this, right? And then there's the scientists who are applying their knowledge of how things work on Earth to interpret, all right, what is this environment we're in on Mars? What does it represent about the past? What can we learn by looking at the elemental composition of this rock? Like those kinds of questions. But these missions are not just U.S. They're not U.S. only, I should say. So at least Curiosity and Perseverance are operated out of the Jet Propulsion Lab in California. But they have instruments that are basically contributions from other space agencies around the world. And so we have colleagues working truly all over the world, all calling in at the same time, working on science together. And so, I do daily rover operations on the missions, and I call in from my computer, and we have a shared, platform to look at the data, to talk about it, to decide what analyses we want to do. And on a daily basis, effectively, you look at the data, you say, all right, this is what we want to study today, and then you send the scripts back to the rover for it to execute the next day. And so, we have people calling in from all over the world during this, and so we try to time it so that on early days, for example, our European colleagues try to call in so that they're not working basically overnight. When we get into like later slide sols or slide days that start kind of late, even on the East Coast, we try to take those shifts so that our colleagues don't have to stay up all night for their rover operations commitments. But it's really humbling also to see, like, I'm talking with people across the world. Some of these folks I've known for over a decade now, and we work on a daily basis together to do science on another world, and we're like discussing these minute details about how do we think these things formed, what does it have to do with the preservation of potential life beyond Earth, and having these really profound conversations over the phone with your colleague in France. And it's really mind-blowing to me that we're able to accomplish this. We do it on a daily basis on these missions. It's something that helps me kind of put into perspective how readily we can all work together if we try.
Yeah, and you bring in your students so that they can get a little bit of that pie. It's also amazing, just because as you were saying, that not only builds you as a scientist, but it builds you as a person, right? It builds you like how to make something, if you're trying to accomplish something ambitious, how to make it happen, how to bring all these people together into one same mission and just go for it, like, and all the process that it needs to happen. Yeah, I imagine it can be very tricky, right? But yeah, just having your students, like, pushing them to get to know a little bit of this world, I think it's super important for them, and I imagine they're very grateful for that. So on that, maybe how important is teaching for you, and what is your philosophy on how do you approach being a professor? Because you could only like, there's definitely some people that just like to do research, right? And they could live their whole life just doing research without having any students at all. But you've taken the time to build a lab, you've taken the time to teach courses and teach special courses, like specialized to what you want to do. Why are you doing this, and why? Yeah, what is the motivation for all this?
Oh my goodness, yeah, such a broad question. So I would just start by saying that UF is actually my second tenure track faculty position. My first one was at Towson University in Maryland, and the program I worked with there, which was a physics, astronomy, geosciences, and science education department, basically we were all combined together. We had an undergraduate only geoscience program. We worked with environmental science. We could have master's students there, but it was 3 times as much teaching as I'm doing at UF. but I wanted that job and went into that job because I care about instruction, because I care about undergraduate education and research experiences and enabling students to pursue their career paths, especially when they never thought it was an opportunity or a possibility. So revealing to people, like, not only are geosciences an opportunity, a career path that a lot of people just don't know about, but helping them to accomplish their goals, especially those who are interested in space science. And I know a lot of people want to work with NASA, but they don't know what that path looks like. And so I tried at Towson and also at UF, I try to serve as a bridge for those students who are interested in those career paths. It can feel overwhelming, and to try to find a way into NASA and or space science in general. And so I try to be that available kind of mentor to help people navigate that. So, I mean, I've always cared about undergraduate education, in part because my undergraduate education and research experiences made me who I am today. Without those, I wouldn't have gone down this career path. I wouldn't have this opportunity, and I wouldn't be able to feed it forward, pay it forward to the students I get to work with now. So, I care about it, and that, I'll tell you, caring about something is one of the greatest motivators to actually trying to do it well. So I care about teaching well. I care about helping my students develop these transferable skills that are useful, whether or not they go into geosciences as their career path or not. I love teaching intro courses because you get this opportunity to show people for the first time geosciences isn't just studying rocks. It's the environment, it's the ecosystem, it's hydrology, it's geology, it's deep earth, it's like into the atmosphere, it's everything. And I really get so much joy of seeing that like realization for people the first time they're like, I didn't realize this was all connected, because I experienced that as well as a college student. So yeah, I want my classes to be relevant to my students. I want them to develop skills that are useful moving forward in their careers, and that's presentations and writing skills and scientific synthesis, right? You need to be able to synthesize the data you see and come to interpretations and conclusions about it. And those are the things that I try to encourage in all of my classes, graduate and undergraduate level.
Yeah, and you talked about the transferable skills, and I'm asking all these questions because I have seen the parallel in engineering, at least, that a lot of people just go to schools and take classes and that's it. And I don't think that's enough. I think you're missing out on the university experience if you're just doing that, and having the opportunity to be involved in these kinds of opportunities, not only like doing really cool research, but really cool research with important institutions that are really doing like the cutting edge work. It's just critical for the development of what you want to become. And and I can say also that I've had that experience with, I've been involved in labs in here in the UF that has made me acquire those skills, and not only the skills, but like knowing what is there to know, right? Because when we enter as freshmen, we don't really know what is there to know, right? And like this curve that we started to get to know all these areas, and then we might get a little bit overwhelmed. It's just, I think the advice of just picking one and picking something that you feel it's exciting, and going for it and try to get as much out of it as possible. I think that's super valuable for people that just thinking university as just sitting in classes and listening to lectures and that's it. I think you really need to get those skills, and because that's at the end what you're gonna do in the whatever you end up doing after. Probably you're not gonna work full-time or as a lecture listener, right?
Yeah, right. If you find out how to get that job, let me know. I definitely see what you mean with like sort of having students engage with their education, right? So it's not just sitting in lectures and listening, and I think that a lot of classrooms have moved away from that model. and you know, there's so many ways to find out which faculty in the programs that you're taking classes in, which faculty are doing more than just lecturing, who have flipped classrooms, who have authentic research experiences in their classes, right? So that you can get an engaged education instead of necessarily just sitting and listening. And I would say that even if you, for example, don't think, okay, so say you take one of my geology courses, but you're not going to be a geoscientist, you know, that's not your career path. That's fine.
Mm-hmm.
You can still get all of these skills from one of these classes, right? We do these authentic research experiences where you go out and you learn to use like the field equipment that's common to a geologist. You learn to collect data, to synthesize it. You're at the time you're, you know, presenting this work, you're honing your presentation skills and your writing skills, which are universally important to career paths beyond whatever your education goals are. And so it's not just like take these classes because you got to take them. It's about getting experiences that enrich your experience, not just your education, but your life, right? You have more context, more empathy and appreciation for all of these fields, you know, the sciences, humanities, liberal arts, like the whole thing. When you experience all of these different projects that allow you to have, I think, a deeper respect for kind of the human experience. You get to learn what it's like to be in someone else's shoes for a bit, and it doesn't necessarily have to be in a hardship way, but I think it makes one more empathetic
Mm-hmm.
to people in general, because you're seeing the breadth of experience. I know it seems very, you know, elevated to say that taking a geoscience course will make you more empathetic to the human condition, but I'm using that, of course, as a geoscientist as an example to like take things that are outside of your comfort zone, take classes or participate in experiences that are outside of what you would normally just say, okay, I'm going to do A, B, and C. Go see what X, Y, and Z look like. Just see what they look like.
Mm-hmm.
You don't have to, it's not necessarily your career, your path, but take it from me as an astrobiologist who works on Mars missions, that when I went to college, I didn't know geosciences was a career path.
Mm-hmm.
I had taken AP biology, so I knew I liked biology, and I said, all right, I'll be a biologist. And when I got to college, I said, you know, maybe I want to be a medical doctor, so I'll start down the pre-med path. And while all of these are excellent careers, finding your passion is hopefully one of the things that you're doing while you're at university, while you're in college. Find the thing that makes you want to get up and keep doing that work every day. And I love this job, and it was a very long path to get to it, and certainly not without challenges, but I love getting up and doing this job every day. And I certainly had people who helped me on my career path to realize I liked geosciences and that I wanted it to be my path. And just by taking these different experiences and seeing what was down those roads, I think that really helped me to get to this point where I am extremely happy with what I'm doing. And it motivates me not just to get up and do research on Mars every day, which doesn't take a lot of motivation on its own, but to want to come in and instruct others, teach others, show them that these are opportunities. All of that has become just like, there's not really a divide between my personal and professional life in those capacities, because it's all just Amy. It's all just what I do and what I care about. And being able to do what you're passionate about every single day is an absolute blessing.
Mm-hmm. Yeah, and I think people need to be. You were talking about this elevated view of studying geology, and I think you should have that view in everything. That's at least part of the reason why I'm doing this. I think almost everything can be interesting, right? And you can find the beauty in everything. You just gotta look deep enough to find it, right? And you gotta stop and appreciate the meaning of all this stuff. And I do find that beauty in engineering too. And yeah, I think what one needs to do is, as you were saying, just be courageous and go for it, right? I think, yeah, just having an opportunity to be in university and having an opportunity of choosing, I think it's a blessing. And just being able to explore all the opportunities that this institution can bring you. And yeah, one should try to take advantage of them as much as possible. So on that note, we've already talked about courage and just going for what you care about. Is there like a final advice you would like to give to students, maybe undergraduates, maybe freshmen, maybe high school students that are starting their careers and maybe don't really know what's out there and what their career will be? It doesn't have to be a career advice. It can be anything.
Yeah. I mean, I think, number one, your career can change over the course of your life, right? So don't feel like if you select something like this is what I'm going to do forever, it doesn't have to be, and it shouldn't have to be if you don't want to. But I think the biggest thing I would say is reach out to anyone and everyone who you think can help you achieve whatever your goal is at that time. Mm-hmm. So oftentimes, at least in my experience, it's been reaching out to professors, research advisors, people who have more experience than me, who can help me not only navigate that path of where do I want to go and what do I want to do, but to open your eyes to opportunities and possibilities that you didn't know were options. I didn't know I could be a geoscientist leaving high school, and now it's my entire career and my passion. So reach out, ask for opportunities to work in labs, to get internships, to experience different pathways so that when your career does start to settle, and it may never completely settle, you've at least seen what your options are, and you can hopefully find your passion and live it every day and do good work worth doing.
Thank you.
Absolutely. As a kid, I always kind of pictured, looking up at the stars, that someone was out there on a world somewhere looking up at the stars in their sky and thinking, I wonder if someone is out there. And so the two of us thinking this at the same time, light years apart,